Okay, welcome here to a recorded lecture here for Chapter 7. Again, due to us taking the exam this coming week and not having lecture obviously on that day, I'm going to do a recording here for Chapter 7. Again, that way we could try to keep on track here with some of the topics and stuff like this. So we're going to go here to Chapter 7, which is talking about basically equations, chemical reactions. We're going to talk about balancing equations. We're going to also talk about different types of chemical reactions. We will also talk about some calculations involving chemical reactions. So let's get started here. So the first thing we're going to really talk about is actual chemical equations. And we do use chemical equations to represent a chemical reaction that takes place. When we look at a chemical equation, there's really two parts to it. There's the part on the left-hand side of the arrow, and the part on the left-hand side of the arrow are what are referred to as reactants. And reactants are really our starting material in a chemical reaction. They are the things that are going to come together really to have that chemical change occur. And what they end up forming is what we see on the right-hand side of the arrow. The right-hand side of the arrow is what are referred to as products, which are, again, what is formed as a result of a chemical reaction. Remember, chemical reactions are really chemical changes. So basically what we start with and what we end with are two fundamentally different things. And again, they can't get back by any type of physical means. So these are typically what we see in a chemical equation. We also see some other things in this chemical equation, or sometimes in just general chemical equations. In addition to sort of the formulas for the different reactants and products, we oftentimes will see written, sort of in this area next to the formulas, a couple of descriptions of what state things are in, what sort of physical state they're in. If you see like an S, that represents that it's in the solid state. If you see an L, represents it's in the liquid state. If you see a G, represents it's in the gas state. Another very common sort of symbol that we see down there is actually AQ, and AQ means aqueous. And basically what that means is it's a water environment. And it's really a solution. And sometimes people have sometimes a question of, isn't that L basically? We see L, and that's like a liquid. And we see AQ, which if you look at it, it is really a liquid state. And there is a difference between these two symbols. Now, so for example, if you had just water by itself, all by itself, that would get the denotation of L because it's a pure liquid. There's nothing else mixed with it. Now, if you take that water, which is a pure liquid, and you add some sodium chloride, which is, say, a solid, what will happen is if you put those two guys together, the sodium chloride will dissolve. So sodium chloride, like salt, you put a little bit of salt in water, you can mix it up, the salt will dissolve. And what you end up with is not water anymore, because it's not water as a pure substance, but you now really have a mixture. And what you have really is a homogeneous mixture. If you remember, a homogeneous mixture is really what we call a solution. And that's really what sort of the aqueous symbol means. It means basically you have a solution. And what you would have is, again, not water as the solution, but you would actually have a sodium chloride solution. Again, getting that is a bad Q, aqueous symbol there. And again, so that's the real difference between sort of something that has the liquid sort of state and the aqueous state. Again, liquid is just one substance by itself, and aqueous is usually a solution, which usually implies that you have sort of dissolved something with something like water to make that solution. Other common things that we see in equations, actually a lot of times will be found like on top of the arrow. For example, you may have like water written up there, and that sometimes would imply that you're dissolving something in water. You may actually have something written up there that's a catalyst. And a catalyst is something that will speed up a chemical reaction. Important thing about a catalyst is it's not a reactant and it's not a product. And it actually does not get used up in the reaction. It's actually just there to do this one thing, just to actually speed up that chemical reaction from happening. It's just a box the reaction part there. And a catalyst could be something like a metal, like platinum. It could actually be something like an acid, which sometimes is abbreviated like H+, you'll see on top of the arrow. And it can be some other things as well. Another common symbol that you sometimes see on top of the arrow is like a little delta symbol. And usually if you see that on top of the arrow there, that usually represents heat is basically being applied. So these are common things that we see in an equation. One main important thing that we're going to talk about obviously here in this chapter is whenever you have a chemical equation, it does need to be balanced. And that is usually important. Pretty much an equation is for the most part useless to you if it is not balanced. What does a balanced equation mean? It's a simple idea of conservation of mass, conservation of elements. Basically, you need to have the same number of elements on both sides. Now, these elements don't have to be identically in the same location, and they probably will not be. But for example, if we look up here at this equation, there are 2 up in front and 2 on the bottom. That gives us 4 hydrogens on the left-hand side. We see the same thing on the other side. 2 times 2 is 4 hydrogens. In terms of oxygen, that 2 on the bottom means there are 2 oxygens on the left-hand side. And over here, 2 times down here would actually be 1, gives us 2 oxygens on the right-hand side. So although we did make a different compound on the right-hand side there, we still have conservation of all the elements. If we start with 4 carbons, for example, we should end with 4 carbons. Again, they may be in different parts or different formulas, but we should always end up with the exact same number of elements on both sides. So let's talk about a couple of ways that we could go about balancing equations. So for example, if you happen to be given something all in words, the first thing that you do want to do is really write out all the correct chemical formulas. And that sometimes is a really key sticking point for people. They never sometimes get the right chemical formulas like we talked about with nomenclature. And then they're trying to balance this equation, which frankly will never balance because they're really not starting with the correct formula. So it's really important if you happen to need to start all the way back with just words and turn them into formulas, that the steps that you follow is pretty much start with the formulas, forget about the balancing part of the equation. You just want to make sure you got to start with all the correct chemical formulas for everybody. That would be representing what is sometimes referred to as the unbalanced equation. The next thing you want to do is balance the actual equation. And here's the most important thing. The only thing that you can change are the coefficients that come in front. So for example, here, coefficients, those are the numbers that come in front. So for example, if I was going to do nitrogen gas plus hydrogen gas makes ammonia, which is NH3, the first thing that I did was put in there pretty much all the correct chemical formulas. I'm not going to worry about, if it's balanced or not balanced. The next thing I want to do is actually get to balancing. And I personally think that, it's helpful when you get to this part to make a little table. And by a little table, I mean, you just frankly list all of the elements that are involved. In this case, it's just nitrogen and hydrogen. And, on the left-hand side, that's the reactant side. On the right-hand side, that's the product side. And just take a little accounting of what you got going on. So for example, my example here on the left-hand side, I have 2 nitrogens from here. On the right-hand side, I only have 1 nitrogen. Left-hand side, I have 2 hydrogens. Right-hand side, I have 3 hydrogens. So this gives us a good approach of, where we should maybe begin. Again, the only numbers we could change are the numbers that come in front of the formulas, never the subscripts, which are the smaller numbers. We never put a number in between or anything like that, but we could only really change those numbers that come in front. And we do that by taking what we think will help us balance it. So here we can look and see, probably the easiest thing to start with would be the nitrogen. I got 2 on the left, but only 1 on the right. I could simply fix that by putting a 2 here on the right-hand side. And now I really didn't do anything to the left-hand side, but the right-hand side will now change. So now instead of 1 nitrogen, I have 2 times 1, which would give me 2. For the hydrogen now, I have 2 times 3, the subscript, which will now give me 6. And much what happens when you start to balance an equation, you fix one thing, something else gets messed up. So I can now easily go back to the other side of the equation here and see my nitrogens are now balanced. And I can simply fix my hydrogens by putting a 3 in front of the H2. That now gives me, again, 2 nitrogens. 3 times 2 is 6 hydrogens. This would be the balanced chemical equation at this point. Again, the only things that I changed are the numbers that come in front. And again, none of the other ones. I also have this nice little table here that helps me make sure that it is truly balanced. The last thing that you should really do is to make sure, obviously, that everything is balanced. But when you're done, there's really 2 things that need to be done or made sure is done. And the first thing is, when you properly balance an equation, all the coefficients need to be whole numbers. And they need to be the simplest set of whole numbers. So what does that mean, the simplest set of whole numbers? That means there's many ways you could balance an equation. Some people may see bigger numbers, and it may absolutely balance the equation, have the same number of each element on each side. And it may result, for example, in a made-up sort of guy here. Maybe we had a coefficient of 2a plus 4b, and we'll just pretend again in this case that this is all balanced at this point. When we look at these coefficients, although it is balanced at this point, we can actually go through each of these coefficients and really reduce them down by 2. And that's what you should do. So if you can reduce all the coefficients down by a common number and still have a whole number, then you should definitely do that. So if we divide everything by 2 here, we would get really the properly balanced equation that looks something like this. So again, this does sometimes happen. Sometimes, again, people can see sort of larger numbers versus smaller numbers. And you can, if you could go through and reduce down all your coefficients by a common number, that is the proper way to balance it. And again, everybody needs to be a whole number when it's all said and done. All right, so why don't you take a second here and balance this equation. Okay, so let's see how you're doing. Again, I would approach this the same way. We're going to make a little table. So we got nitrogen, we got oxygen, we got hydrogen, reactant side, product side. Here, doing some accounting, we got 1 nitrogen on the left, 2 on the right, 1 oxygen on the left, 1 on the right, 2 hydrogens on the left, and 2 hydrogens on the right there. Looks fairly straightforward here. We are pretty much balanced except for nitrogen. So this tells us we should probably put a 2 over there in front of the nitrogen on the left. That now changes the everything on the left-hand side. We now end up with 2 nitrogens. We multiply the 2 to the oxygen that's behind it. That also gives us 2 and we still have 2 hydrogens. Again, here we fixed the nitrogen, but we kind of messed up the oxygen, I'm sorry. So that then tells us we should go to the right-hand side and fix that by putting a 2 in front of the oxygen on the right. Now on the right-hand side, we still have 2 nitrogens. Oxygen's 2 times 1 is 2. Hydrogen now is 2 times 2, which is 4. So we're almost there. We've now got the nitrogen and oxygen good. We now will go back to the left-hand side and put a 2 in front of it. And that should do us, I think, 2 nitrogens. We now have 2 times 1 oxygen, and 2 times 2 is 4 hydrogens. We are now properly balanced here. And that would represent, again, our balance equation, exact same number of elements on each side. Again, the only thing here that we changed, as you can see, are just the coefficients. Just like most things in chemistry, again, if the coefficient is not written, it's assumed to be 1, by the way. And then we have the 2 there. Let's take a look at another one here. So take a moment here and see what you come up with. All right, so let's see how you're doing. So again, same approach, which is a pretty good approach here. That way you can kind of keep track of things. We got the reactant side, we got the product side. Let us take a look at each of the elements that we got going on here. So in this particular case, we have carbon, we got hydrogen, and we have oxygen. Again, on the left-hand side, we have 3 carbons. Right-hand side, we have 1 carbon. Left-hand side, there are 8 hydrogens. Right-hand side, there are 2 hydrogens, 2 oxygens on the left. And on the right-hand side, we have 2 oxygens there and 1 more there. So that gives us 3 oxygens in this particular case. All right, so again, probably the easiest thing to start with would be the carbon. So we could simply put a 3 over here for the carbon on the right-hand side. That now gives us 3 carbons, gives us 2 hydrogens. Now in terms of the oxygen, again on this first arrow here, that is 3 times 2, which is 6. And we still got 1 more oxygen hanging out over here, which is 7, if I did my math right there. We fixed the carbon, so probably again, the next easiest thing to fix would be the hydrogen in this case. We could simply go to the right-hand side and put a 4 in front of it. When we do that, again, keeping track of everything on the right-hand side, because we didn't do anything to the left, so it stays the same. We still have 3 carbons. Hydrogen now is 4 times 2, which is 8. And now our oxygens on the first guy here, 3 times 2 is 6. And now we have 4 times 1 on the second arrow here. So that is 6 and 4. I think they call that 10. And now we got carbon and hydrogen all balanced. So it's time to go to the left-hand side here to fix our oxygen, which means we just need to put in there a 5. That gives us on the left-hand side 3 carbons, 8 hydrogens. 5 times 2 here is 10 oxygens. And again, this would represent your balanced chemical equation, which simply just means we have the same number of elements on both sides. All right, another one here. Why don't you take and try here? Again, this would be one where we talked a little bit earlier. We have diboron trioxide reacts with water to form boric acid. And what I mean by that is this is one, perhaps you have everything given to you in words. So the very first thing that you would want to do is go through that and basically write the unbalanced equation with all the correct formulas, forgetting about the balancing part. So diboron trioxide, those prefixes tell us that that is a type 3 compound. and two nonmetals together. So that is B2O3 plus H2O, which is water, makes BOH3, which is our boric acid. So take a moment here and see what you come up with. So again, working it the same way, we're going to go with a boron, an oxygen, and a hydrogen. Looks like all the elements we got going on here. Reactant side, product side. Left-hand side, we got two borons. Right-hand side, we got one. Left-hand side, we got, again, three oxygens there, plus one more there. Gives us four oxygens. On the right-hand side, this OH is in parentheses. This three on the outside gets distributed to each of the elements that are inside, which means we do have three oxygens on the left, two hydrogens on the left. I'm sorry, three oxygens on the right there, two hydrogens on the left, and three hydrogens on the right. Not a lot to work with here. Might as well start with the boron, since boron and everybody else is tied together all in one thing on the right-hand side. Let's start there by fixing the boron by putting a 2 in front. So what does that do for everybody? Well, that gives us the two borons that we need. Now, in addition to distributing the 3 to each of the guys in the parentheses, we also have to then multiply each of those guys by the 2 on the outside. So essentially that gives us 2 times 3, which is 6 oxygens, and 2 times 3, which is 6 hydrogens. And really the reason for that is, if I just draw it out, the 3 OHs, as you can see, there is 1, 2, 3 oxygens, 1, 2, 3 hydrogens, but there's 2 sets of those. So that is where our 1, 2, 3, 4, 5, 6 comes from. 1, 2, 3, 4, 5, 6. So again, you got to distribute in and then distribute out to the coefficient. Clearly, at this point, we can't do much more on the right-hand side since everybody's tied together. So we need to now look to the left-hand side to try to fix it. Perhaps the next easiest thing to go with would be hydrogen, because oxygen's in a couple different places here. So to fix the hydrogen, we can then put a 3 in front of the hydrogen. That gives us 2 borons. In terms of oxygen, that is 3 for the first arrow. Also need to multiply the 3 times 1 on the second arrow. That gives us 6 oxygens. And then the 3 times 2 is 6 hydrogens. By actually just putting the 3 to fix the hydrogen, it actually also fixed the oxygen. And that also happens a lot when you're balancing. Sometimes just balancing one other element will actually take care of some others as well. So that works out very well. Again, here we do have our balanced chemical equation. All right, take a look at this one, see what you come up with. Okay, let's take a look. And here we got reactant side, we got product side, and we got N, H, and O. Left-hand side, we got 1 nitrogen. Right-hand side, we got 1 nitrogen. Left-hand side, we got 3 hydrogens. Right-hand side, we got 2 hydrogens. Oxygen on the left there is 2. On the right, again, we got oxygen in a couple other spots, and that would get us 2. Looks like everything is balanced here except for hydrogen. So clearly a good place to start. We have 3 on one side, 2 on the other side. So the common number between 3 and 2 is 6. To get my hydrogen to 6 on the left-hand side, I need to put a 2 in front of it. To get my hydrogen to 6 on the right-hand side, I need to put a 3. And let's see what that does to everybody else here. That gives us 2 nitrogens. Hydrogens, 2 times 3 is 6. Oxygen is 2 in that case. Right-hand side, we got 1 nitrogen still. Hydrogen, 3 times 2 is 6. And oxygen, again, on the first arrow here, we have 1. On the second arrow, we need to take that 3 and distribute it to the guy over here. And that gives us 3 and 1, which would be 4. So here we really did fix the hydrogen, but pretty much messed up everybody else. Probably the next easiest thing to balance at this point would be the nitrogen. We could simply do that by putting a 2 in front of the nitrogen on the right-hand side. When we do that, that then gives us 2 nitrogens. Hydrogen is 3 times 2, which is 6. Oxygens now, again, in the first guy here, we got 2 times 1, which is 2. Second guy is still 3 times 1, which is 5 total there in that case, if I'm not mistaken. So we got 2 and 3 is 5. We've now balanced our nitrogen. We have now balanced our hydrogen. We need to fix our oxygen. Now, at this point, I'm just going to rewrite this for a little clarity here. So at this point, we've clearly have put coefficients down, pretty much in these locations. You never, in most cases, want to go back, obviously, and start changing those numbers because that is going to basically start messing up everything. So really, the one place we got left to work with is basically right here. So we essentially won't need to turn that 2 into a 5. And how can we turn a 2 into a 5? Well, one way you could do it is actually you could use a fraction to balance it. And you could do something like 5 divided by 2. When you take 5 divided by 2 and times it by the 2 that's on the bottom there, the 2's canceling, you actually end up with 5. So technically speaking, at this point, we have 2 nitrogens, 6 hydrogens, 5 halves times 2 gives you 5 oxygens. And technically speaking, this equation is balanced. Now, you might remember earlier I said that there's basically 2 things when you balance an equation that you need to make sure is sort of true. The first thing is you need to make sure that you have all whole numbers, and they are the simplest set of whole numbers. Clearly here, a fraction is not a whole number. So this is a good example that illustrates you can absolutely use a fraction to balance an equation. Oftentimes happens when you have, like, say we see here, oxygen and 2 things on the right, kind of oxygen in its natural by itself form on the left-hand side. You oftentimes will need a fraction. You need to clear the fraction for it to be properly balanced. And then to do that, to clear a fraction, you need to multiply by everything by the denominator, the guy on the bottom. In this case, we would multiply everybody by 2. Again, not just the fraction by 2, but everybody in the equation by 2. And if we do that, we now end up with 4NH3 plus 5 halves times 2 is 5 O2, goes to 2 times 2, which is 4NO, plus 2 times 3, which is 6H2O. That means that if we did not mess up here, we should still be balanced. So let's take a look at our table here and see how we're doing. So if we take a look at it, that one. Starting on the left here, nitrogen 4. Right-hand side, nitrogen 4. So that's good. Hydrogen, 4 times 3 is 12 on the left. Hydrogen on the right-hand side, 6 times 2 is 12. Lastly, oxygen, 5 times 2 is 10. And in the last one here on the right, there are 4 oxygens there and 6 more there, gives us 10. This would be the properly balanced equation here for this particular reaction. So you can absolutely use a fraction to balance an equation. The only deal is you do need to clear the fraction to get yourself to the properly balanced equation. Now, sometimes people go, how do I know what fraction I need to use? And there's really a simple sort of formula for determining sort of the fraction that you need to use. And that is, if we go back to before we balanced it, we had something like this. And at this point, if you remember, in terms of just the oxygen, on the left-hand side, we had 2. On the right-hand side, we had 5. And that's what we need to turn this 2 into a 5. So when you do the fraction, we chose 5/2. The top number is always the number you need. So again, here, we needed that top number to become 5. The bottom number should always match that guy right there. So it should always match that number that's on the bottom. And that's pretty much how you could choose the correct fraction to use. Top number, always the number you need it to be. Bottom number should always match the subscript that's on the bottom. And that's because then the subscript will properly cancel out and leave you with just the numerator, which is the number that you need. So these are ways to balance equations. And these are the steps that you want to follow. Again, the ultimate goal here is to make sure that we do have the proper number of elements on each side, which is the same number of elements on each side. One last thing before we kind of move on from balancing equations is, sometimes we do get equations. Let me see here. I can give it a go here off the top of my head. We'll do that. And let's see how we did here. Give it the old college try. Do that. And what we got going there. Okay, let's see here. Okay, so just to make sure here that looks good. Okay, so sometimes when you look at some equations, you oftentimes will have some of those polyatomic ions in it. So for example, if we look at this one, that's nitrate, and that's nitrate, that's sulfate, that's sulfate. And sometimes, you definitely could go element by element like we did before. The problem with doing that sometimes when you have a lot of polyatomic ions in is there's a lot of like multiplying in, multiplying out and stuff like that. It sometimes makes it difficult to keep track of everybody. And sometimes when you do have sort of your polyatomic ions that look the same on both sides, it's easier to keep them together and balance them as a whole unit. So what I mean by that is if I was to balance this equation, I would first look at it and go, I got 2 nitrates on the left. I only have 1 nitrate on the right. I'm going to fix that by putting a 2 in front of it. That 2 will now give me 2 nitrates. It also does mess up the sodium, but I would then go to my left-hand side and see I actually have 2 sodiums. And actually at this point, this thing would be balanced. We have 1 sulfate, 1 sulfate, 1 calcium, 1 calcium. So sometimes it's a lot easier to do that. For example, maybe I'll try to do a better one here. Let's see. We'll try this and see if this comes out any better. Then that means I will end up with and so again here, we could kind of take sort of a similar approach. We will see, for example, if we look on both sides, we again have our nitrates, we again have our sulfate. And again, in this case, you could pick one of those polyatomic ions to sort of start with, if you like. So for example, if we wanted to, we could start with the sulfate. We have 3 on this side. We have only 1 on this side. So we could simply fix that by putting a 3 here. When we do, that gives us 3 sulfates, also now gives us 3 calciums, which tells us where to go next. We would then want to put a 3 in front of the calcium on the left to balance it. That 3 balances the calciums, but then we have 3 times 2. gives us 6 of the nitrates, which means if we go to the right-hand side to fix that, we put a 2 in front of the nitrate, giving us 6 of them. Also gives us 2 irons, which is okay because we have 2 irons on that side. So sometimes it's quicker, it's faster, and it's easier when you have equations that contain polyatomic ions on both sides to try to keep them together and balance them as kind of whole units. Okay, so that talks about balancing equations. Let's now talk about basically different types of equations, or reactions, really, different types of reactions and different ways to classify reactions. There's kind of 2 big categories of reactions. One are redox reactions. And redox reactions means oxidation and reduction. And really what those guys mean is oxidation means loses electrons. Reduction means something gains electrons. People sometimes remember this by going Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. So you could choose either one there if you like. So under redox reactions is a number of different types of reactions that occur. The other kind of big classification we'll talk about in terms of reactions are double displacement reactions. And those are a little bit different, and we'll see those in just a bit. So first off here, if we look at this one, this is sodium plus chlorine makes sodium chloride. And this is really a redox reaction that's going on. If we look at sort of the charge, which is really was referred to as the oxidation state, but we'll call it charge for now. Sodium all by itself really does not have a charge. Chlorine in its natural state does not have a charge. Remember that these things really only gain a charge when they come together. And what's going to happen in this case is sodium is going to transfer the electron over to chlorine, and sodium now will become +1 and chlorine will become -1. And it's that point on the right-hand side when they come together that they actually do make a charge. So how can you determine, what is going on in terms of oxidation reduction in a particular reaction like this? A very simple process of like a number line. To the right of 0 is positive numbers, to the left of 0 is negative numbers. And when you lose electrons, you become more positive, and that's because you have more protons than electrons. When you gain electrons, you become more negative, and that's because you have more electrons than protons. And what that means is if you are on the number line here and your kind of oxidation state or charge is moving more negative, that thing is going through what is known as reduction. If you're moving along here on the number line to a more positive direction, that means that guy is going through oxidation. So very simply, we could see what's happening with the sodium. What's happening with the sodium is it is starting at 0, which is here, and it's ending at +1, which means it's moving in this direction. So in this particular case, the sodium is losing electrons, and this guy right here is going through what is known as oxidation. The chlorine, on the other hand, if we follow sort of what is happening with it on like the number line here, it also is starting at 0. And that would be like here. And on the other side, it is ending at -1, which means it is heading in this direction. And heading in that direction means that the chlorine is actually going through what is referred to as reduction, is gaining the electrons. They always happen together. So something is being oxidized, something else is being reduced. And this is really a redox reaction when we look at a reaction like this. So this is sort of a classic sort of redox reaction. And another example, and again, oxidation reduction is a long form of what people call redox reactions. We look at another example here. This is magnesium, again, by itself, means it really has no charge or oxidation state. Oxygen, same thing, is not combined with anything, has really no charge or anything like that. When they come together again, and to make this ionic compound, this is where they get a charge. The magnesium now becomes +2. The oxygen now becomes -2 at this point. And again, if we want to kind of determine, we could recognize this as sort of a redox reaction, what is happening, we could simply follow, again, we'll start with the magnesium starting at 0, which would be here. It is ending at +2, which means it is moving in the positive direction. And that should tell us that the magnesium is going through oxidation, becoming more positive because it's losing those electrons. The oxygen, on the other hand, is starting at, actually, we'll use a different color here. Grab that one. Oxygen starting at 0 also. By the way, they won't always start at 0, but they're starting at 0, ending at -2, which means it's moving in this direction, which is more negative. And more negative means that the oxygen here is going through what is referred to as reduction, which means it is gaining electrons, which is why it's becoming more negative, because it has more electrons, which are negatively charged, than protons, which are positively charged. So again, this guy on the bottom is also considered a redox reaction. Now, you can also have oxidation that involves two nonmetals. And there's a couple other definitions of oxidation and reduction, which we'll touch upon here. But we will also see when we start talking about organic chemistry. So in organic chemistry, it often deals with carbons, hydrogens, oxygens, and elements like that. It often deals with nonmetals. So sometimes we don't really look at gaining or losing electrons when we're dealing with sort of organic compounds. We look at gaining or losing oxygen or hydrogen. So one definition or another definition of oxidation is as you go from the reactant side to the product side, if somebody gains more oxygen atoms, it's going through oxidation. If somebody loses more oxygen atoms, it's going through reduction. There's also a definition for hydrogen. If something loses hydrogen as it goes from reactants to products, it's also a definition of oxidation. If somebody gains hydrogen as it goes from reactants to products, that is also a definition of reduction. So here, if we look at it, our sulfur on the left-hand side had 2 oxygens, sulfur on the right-hand side had 3 oxygens. The sulfur actually gains oxygen as it goes from left to right. And that means that the sulfur here, or the SO2, would be going through oxidation. By default, this guy would be going through reduction. Same thing here. Copper had an oxygen on the left, none on the right. It actually lost oxygen, which means that this guy here would go through reduction. And this guy here would go through oxidation. Now, in this particular case, there actually is a metal, and you could actually do the charge or oxidation state like we did before. The oxidation state on the copper here is +2. Oxidation state on copper by itself is 0. So again, if we did our number line, because we do have a metal present, we would be starting at +2, which is here, ending at 0, which means it's going in the negative direction, and it is going through reduction. So again, we can use kind of both definitions here to determine that the copper, in this particular case, the copper 2 is going through reduction. The nice thing about oxidation and reduction is if you can identify one of the guys as either going through reduction or oxidation, by default, the other thing should be going through the opposite sort of process. So if you identified the first reactant as being reduced, you don't even have to really think about it. The other guy should be oxidized, and vice versa. If the first guy you looked at was being oxidized, then by default, the other guy should be reduced. And again, we'll see sort of these definitions a little bit more. And here's the hydrogen base one. I kind of jumped a little earlier there. But again, we can look at hydrogen as well. And here we see carbon going on the left-hand side with 4 hydrogens, carbon ending on the right-hand side with no hydrogens. So the carbon here is going through oxidation, while the oxygen actually on the left-hand side had no hydrogens, but on the right-hand side did get hydrogens. So the oxygen is actually going through reduction here. And again, we'll see that sort of oxygen, hydrogen sort of definitions a lot more when we get into organic chemistry. Now, there's multiple ways you can sort of classify reactions. And as I mentioned before, the redox reactions are sort of a big umbrella of reactions. And underneath those are some other sort of classifying or ways to classify reactions. And really, when we look at reactions, there's really 3 driving forces, for why a reaction takes place. So sometimes people ask, why does a reaction actually take place? And one of the important things for why sort of a reaction takes place is that the formation of an actual solid being formed. So what that means is we have mixed a couple of things together in some type of solid form. It's also referred to as a precipitate, sometimes abbreviated as PPT. And that means that, again, you mix those things together, some type of solid form. Water, the actual formation of water, is really another driving force as to why, when you put 2 things together, a reaction actually takes place. And lastly here, kind of what we were just talking about, a redox reaction, which involves the transfer of electrons, are really those driving forces for why reactions actually take place. So as we go through these different types of reactions, we will see each of these things sort of happening. And again, that's really why these reactions do take place. You can sort of cross-classify reactions, and we'll take a look at a couple here and explain that. First off, the first type of reaction, which is really under the classification of a redox reaction, is what's referred to as a synthesis reaction or a combination reaction. And a synthesis or combination reaction pretty much sounds like what the description says. It's a combination. Basically, as it shows here, we take 2 things and make 1 thing. So we combo or combine those things into 1 thing. Here, 2 things, hydrogen and oxygen, makes 1 thing, water. Sodium and chlorine makes sodium chloride. 2 things make 1 thing. So these are classic examples of synthesis or combination reactions. You may be saying to yourself, didn't we just see this one? And wasn't this a redox reaction? And the answer is yes, it is. Again, redox reactions are sort of the big umbrella, and underneath that umbrella falls a specific way of classifying a reaction as a synthesis or combination reaction. And again, we see here, like we talked about, sodium is 0 and 0, +1, -1. And again, the sodium being oxidized, the chlorine being reduced. Same thing here with the water. This is actually 0 for the hydrogen, 0 for the oxygen on the left. Hydrogen on the right is actually +1, and oxygen on the right is -2. Again, if we lay up our number line here to quickly verify that it is a redox reaction, looking at the hydrogen, it goes from 0 to +1, becoming more positive. So this guy is being oxidized, or going through oxidation. If we look at the oxygen, on the other hand, the oxygen is starting at 0 as well, ending at -2, which means it is traveling that negative direction. And again, going in that negative direction tells us that the oxygen in this case is being reduced or going through reduction. So most people would probably classify both of these reactions as a synthesis or combination reaction. It is not incorrect to classify as a redox reaction, but again, a redox reaction is sort of like the big classification. The more specific classification would be a synthesis or combination reaction. Another reaction, which is basically the opposite of the one we just saw, is a decomposition reaction. And a decomposition reaction is basically, as it shows here, we take one thing and break it apart into two or more things. So one thing into two or more things. We see that here with water. If you run an electrical current through water, it will break it apart into hydrogen gas and oxygen gas. One thing makes two things. If we heat up some mercury 2 oxide, we'll get some mercury liquid and oxygen. One thing makes two things, your classic decomposition reaction. So synthesis combination reaction puts it together. Decomposition, again, basically the opposite, breaks it back apart. And so they're kind of opposites of each other. Again, these things here are also redox reactions as well. These can, again, be classified as redox reactions. Let's just look at the bottom one. The mercury here actually has a +2 charge. Oxygen has a -2 charge. On the other side, mercury is by itself. So again, when things are by themselves, really no charge, or really it's more what is referred to as the oxidation state is 0. Again, if we just use our basic little number line here and we follow the mercury, for example, mercury starting at +2, which would be out here, mercury ending at 0, which means it's actually going to the left and becoming more negative. That means that this mercury 2 oxide is going through reduction or being reduced. And we can verify the oxygen by looking at the oxygen, where it started and where it ended in terms of its oxidation state. So the oxygen started at -2, which would be over here, and ends at 0, which means it's going in that direction, the more positive direction. That tells us that it is being oxidized. So it is actually the oxygen here that is being oxidized. I might have misspoke earlier. It's actually the mercury 2 part of this, not the whole thing, but it's actually the mercury 2 part of that is going through the reduction or being reduced, and it's the oxygen part that is being oxidized. So again, this is another way to classify this reaction. Most people, again, would probably classify as a decomposition reaction, and it does still fall under sort of the big umbrella of redox reactions. Another reaction here is a single displacement reaction. Sometimes people call it a single replacement reaction, but basically it has these general formulas here. Let me just kind of explain what they are. A plus BC. So we'll say, for example, A here is a metal. It actually is by itself, which means it has no charge. This is an ionic compound that has a positive and a negative guy. And although the metal does not have a charge to begin with, when a metal gains a charge, we know that it does gain a positive charge, which means when this metal comes in, it's going to kick out the positive guy. When it does so, it will make a new ionic compound that is a positive negative, and it's at that point the guy coming in will gain a charge. The guy that gets replaced comes out by itself, uncombined, and has no charge. And this is a single replacement reaction. You could also have this reaction take place where this guy is actually a non-metal by itself. Also would have a 0 charge. The difference is when a non-metal gains a charge, it actually will become a negative charge, which means this guy will come in and actually kick out the negatively charged guy, making a new ionic compound, positive and negative. And at that point, it will gain a charge, the guy coming in. The guy that gets kicked out again will get kicked out uncombined by itself with really no charge. So if we look at that here, we see the zinc on this case has no charge. This is hydrochloric acid, which is positive, negative. The zinc is a metal, which means it normally will make a positive charge. So it's going to come in and kick out the positive guy. When it does, it's at that point that the zinc gains a charge, a +2, and hooks up with the chloride, which has a -1 charge to make this guy. The hydrogen comes out by itself uncombined as hydrogen gas in this case. So this is a single replacement reaction. And to also let you know, you might guess this is also a redox reaction as well. Again, if we look at the charges here, +1, -1, and 0. On the right-hand side, hydrogen is 0. Zinc is +2 at this point, and that is -1. So again, our simple number line here. Let's take a look at the zinc and see what is happening. So our zinc is starting at 0 and ending at +2, which means it is going in this direction, becoming more positive. So it is the zinc in this case that is going through oxidation. What is happening with the hydrogen? Well, if we look at the hydrogen in this particular case, we see that the hydrogen started at +1 and then ends at 0, which actually means the hydrogen is moving in a negative direction. And that is your definition of reduction. So it is being reduced. What about the chlorine in this particular case, which you might be wondering about? Well, if we look at the chlorine, for example, maybe I choose the right thing here. There we go. We'll go with that one. We look at the chlorine here. Chlorine is -1. And on the other side, it is still -1, which means it is just there. Nothing has happened as it would go from left to right. So there's nothing actually happening with the chlorine. It's not being oxidized, not being reduced. It is what is referred to as a spectator ion, the chloride in this case. And a spectator ion, much like the name implies, if you are a spectator, you are pretty much just watching what is going on. So it's there. It's really there to balance out the charge, but it's really not participating in any type of products being formed or anything of that nature. So single replacement reaction, one guy comes in, kicks out the other guy. We get some new guys that are formed. The last important thing about this is whatever is coming in to kick out. So for example, our A to our B, C. In order for this reaction to take place, whatever is coming in needs to be more reactive than what it is replacing. And if it is not more reactive than what it is replacing, the reaction actually won't take place. So for example, this reaction up here that we've scribbled all over, if we did it with copper instead of zinc, when this copper would try to come in to kick out the hydrogen, copper is less reactive than hydrogen in this case, and we would actually get no reaction. So, you sometimes will have a reaction like this that may not take place because whatever is coming in is less reactive than whatever is trying to replace. That's also a way you could tell in terms of activities and reactivities of metals, for example, if you did these two reactions, you put the zinc into the hydrochloric acid or you put the copper into the hydrochloric acid, you see the zinc reacted, but the copper didn't. That would tell you basically that the zinc is more reactive than the hydrogen. And again, the copper would be less reactive than the hydrogen. Now, those reactions that we just talked about are basically under the big umbrella of redox reactions. So we have under redox reactions, synthesis and combination reactions, decomposition reactions, and single replacement reactions. We're now going to move into the next sort of big umbrella of reactions, which are double displacement reactions. Double displacement reactions have a general formula of AB plus CD, And what these guys are positive, negative guys, positive, negative guys, two ionic compounds basically. And what happens is the two positive guys switch partners. The result of that is you make two new ionic compounds. And that's sort of your big umbrella of reactions. Underneath these, as we will see right now, are what are sometimes referred to as precipitation reactions, where some type of solid forms, and acid-base reactions. So if you think about sort of the previous reactions, and you think about what we saw really happening with those, and you go back to what we saw earlier about the driving forces of reactions. Remember, one was the transfer of electrons. That's like our redox reactions that we've been talking about. The other one is the formation of a precipitate, which is what we're going to be talking about here, our double displacement reactions. And the third one is the formation of water, which is also our double displacement reactions. So here, if we look at this, this is what is referred to as a precipitation reaction. And that's basically when we take two solutions, as we can see by the aqueous symbol here, we get a solid that is formed. So when we make a solid, which again is referred to as a precipitate, that is what is referred to as a precipitation reaction. This is also a double displacement reaction. This is potassium chromate. That's a positive negative guy. That's barium nitrate, which is also positive negative. And what happens is these two positive guys switch partners. So we see that the potassium goes with the nitrate on the other side. The barium ends up with the chromate on the other side. And again, it's really a double displacement reaction, sort of the big classification, but it's also more specifically classified as a precipitation reaction because a solid was made as a result of those two solutions being mixed. So again, what we see happening, as I mentioned, is whoops, wrong button, try that. A double displacement reaction, again, are two positive cations are switching places. And again, that really is your classic double displacement reaction. And again, more specifically speaking here, again, because a solid was formed, that will tell us that it is a precipitation reaction as well. Here is a mixture of an acid and base, and this is sometimes called a acid-base neutralization reaction. And whenever you take an acid plus a base, you basically make two things. You make water and what is referred to as a salt. Now, this is an acid. This is hydrochloric acid. This is potassium hydroxide, which is a base. And here is our water that was formed and our salt that was formed. Salt is a fancy word. I'm not sure how fancy it is, but it is a fancy word for an ionic compound. So this is an acid-base reaction, which is a more specific classification of this type of reaction. But if we look at it, hydrochloric acid, that is a positive negative guy. Potassium hydroxide is a positive negative guy. Again, the two positive guys are going to switch, the H plus and the OH minus. That is where water comes from. So basically the acid provides the H plus, the base provides the OH minus. Those two things make water on the product side. The salt part comes from what's left over. So what's left over here is a potassium and a chloride. And those two come together to make our potassium chloride, which again is what is referred to as a salt. So this is a double displacement reaction, again, more specifically classified as a acid-base neutralization reaction. And it clearly shows what we were talking about in terms of a driving force for a chemical reaction. What did we make? We made water. which again is that driving force for why a chemical reaction takes place. Why is this sometimes called a neutralization reaction? Well, the overall real reaction that's happening is actually this reaction right here. The overall thing that's really happening is the acid is giving the H plus, the base is giving the OH minus, and those two things have an incredibly strong attraction to each other to make water. And neutralization reaction, basically you made water, and that's why it's sometimes called an acid-base neutralization reaction, because no matter what combination of strong acid and strong base you put together, it always results in the same thing. It always results in basically water being formed. If you get down to the heart of the reaction is basically that formation of water. So the last sort of type of reaction we're going to talk about is a combustion reaction. And there are really two types of combustion reactions. And I would say probably 90% of the time, if somebody said, hey, tell me about a combustion reaction, they are probably talking about like an organic combustion reaction. And what that means in organic compounds are usually carbons, hydrogens, and oxygens. Like we see here, carbon and hydrogen, carbon and hydrogen. And the classic components of a combustion reaction is you have O2 on the left-hand side, and it always forms CO2 and water on the right-hand side. So in a classic organic combustion, it's right here, an organic combustion, organic compound, which is carbon, hydrogen, and oxygen, plus O2 makes CO2 plus water. That's like your classic combustion recognition. It's what happens when you light a Bunsen burner, methane, which is this reaction right here, put some oxygen for the surrounding, a little bit of spark, and a lot of times you get fire, you get heat and stuff like that. And that's a combustion reaction, and typically what most people sort of think about. So definitely if you see this, combustion reaction. Now, another more general definition of combustion reaction, which you might see, is basically just there's O2 in the reaction. So that is a basic combustion reaction. For example, earlier we saw this reaction, which we classified two ways. We classified it as a redox reaction and also a combination or synthesis reaction. Technically speaking, this would be classified as well as a combustion reaction because it has O2 on the left-hand side. So again, most people think about combustion in terms of the organic reaction, but the basic definition of combustion is just simply having O2 present in the reaction. So as you can see here, there are multiple ways you can sort of classify reactions, some more specific, some a little bit more broader in terms of their classifications. But to summarize sort of the two big umbrellas of ways to classify reactions and which ones fall underneath them, let me just kind of diagram that for you here. Clear a little space. There we go. So again, under like a big umbrella of those redox reactions, we have more specific ways of classifying them as synthesis or combination, decomposition, single replacement, and really this type of combustion reaction would fall under there as well. So we'll put combustion under there as well. Again, this is also a redox reaction, as we talked about, combustion reaction, a synthesis reaction, this guy up on top here. And then the other big classification are those double displacement reactions, which can be, again, more specifically classified as a precipitation reaction. Precipitation reaction, where a precipitate is made, or an acid-base reaction, where water is made. And again, over here in redox, that's about electron transfers. So when we talked about earlier, again, those three driving forces for reaction: precipitate, water, electron transfer, that gives us all of our classifications of reactions here. I think for now, we're going to stop the recorded lecture here. This is going to be kind of part 1 of chapter 7's lecture. And then we'll pick up with probably another recorded lecture for part 2 of it. So this recording will cover obviously what we talked about there, balancing equation, types of equations. I'll see you on the next one here for part 2.